Okay, I'd like to welcome everybody to this term's Strachey Lecture, which is our distinguished lecture. Before I introduce the speaker, I want to thank our sponsors, Oxford Asset Management, who have been hosting this series since 2015. And if any students or researchers want to meet them afterwards, you can do that during the coffee. One last administrative thing. After the talk, we're going to have a Q&A in here, and we'll have some microphones running around, so if you want to ask a question, we'll do it that way. Okay, so I am super delighted to introduce Shafi Goldwasser. This is about the best speaker I could actually ever imagine, and I think the contents of the room makes this clear that other people concur with this opinion. Shafi is a professor at Berkeley, and the former director of the Simons Institute for Theoretical Computer Science. Actually, she's just stopped doing that, but she retains her role as research director of the Resilience Pod at Simons. And in addition to that, Shafi is a professor at MIT and also emeritus in Weizmann, so she's very many locations. When I decided what to tell you, her awards and accomplishments are so significant that what I decided to do is to read you just a tiny bit from the citation of just a few of her very major awards. And I'm going to start with the Gödel Prize in 1993. So Shafi was awarded that prize for her paper, The Knowledge Complexity of Interactive Proof Systems. And I've shortened these a little bit to not use all of her time, but the citation points out that she and Sylvia Macaulay introduced the concept of interactive proof systems, providing a rich new framework for addressing the question of what constitutes a mathematical proof. Goes on to say that this led to exciting developments, including the resolution of several major problems about the difficulty of finding near-optimal solutions to conflict-level optimization problems. So a Gödel Prize would be pretty much enough for anybody, but Shafi's got two of them, because she had another Gödel Prize in 2001 for her paper, Interactive Proofs in the Hardness of Approximating Cliques, with Feigl, Loewy-Stauffer, and Skedy. And here the citation says that they developed a completely new understanding of when an algorithmic problem is intrinsically hard. With their deep insights and powerful results, they've opened new perspectives for many problems in computer science, for example, in optimization and cryptography. The last one that I'm going to read to you is the Turing Award, which is pretty much the biggest prize anybody could ever get in computer science. And Shafi received that in 2012, along with Macaulay. And the citation says, for transformative work that laid the complexity theoretic foundation for the science of cryptography, and in the process pioneered new methods for efficient verification of mathematical proofs. So Shafi is a member of the National Academy of Sciences and the National Academy of Engineering in the USA, the Russian and Israeli Academies of Science, a foreign member of the Royal Society here, and a bunch of others. She's also got a long list of honorary degrees, including here at Oxford, and we are completely lucky to have her here today, speaking to us about privacy verification and robustness, a cryptographer's perspective on ML. So,
thank you very much.
Good? Do you want it darker? Oh, okay.
So hi everyone, and I'm very honored to be invited for your lecture and also to have received an honorary degree here. And Oxford is so beautiful. It's a little hotter than I thought. So the title's a little different than what I gave originally, but it amounts to the same when you look at the content of the talk. So I'm going to call it Constructing and Deconstructing Trust in AI, totally a cryptographic perspective. So you know, I've given some version of this talk without most of the results that are here, maybe 5, 6 years ago. And at that point, I don't know that I would have used this slide. But at this point, it's very clear that machine learning revolution is really the scientific breakthrough of our times. And that started with deep learning, now with the large language models, has kind of achieved an entire level altogether. And when Leslie was saying about the greatest honor in computer science, I was thinking about these Nobel Prizes now for machine learning people. So, obviously it raises these very deep questions about human versus machine intelligence and whether large language models, this project that Michael Bronstein and I am working on, will even give us the ability to translate non-human communication. People these days are all talking about AGI and superhuman intelligence. There are betting markets about when that's going to happen. You have already the O1 doing very well on competition math, competition code, PhD level science questions. There's a whole benchmark of new questions out there which we don't know the answer for. We all agree, I think, with this slide, and you don't need me for that. The lead-in is to the fact that whether or not we believe that that this is the biggest scientific revolution, it's going to solve the Riemann hypothesis, whatever, we do know already that is huge, not only promise, but for applications, whether it's health, drug discovery, infrastructure, natural language processing, policing, financial markets. And all of this indicates really that there's a major shift of power, which we're all aware of, for those who have data and those who have algorithmic expertise. And one can argue in debate whether data is more important or algorithms are more important, but what is very clear is that's where the power lies. And all that's beautiful. The problem that this talk is about is, should we really trust models to the extent that we are very rapidly trusting? We don't understand and we don't control. And I think, at least for myself, maybe because I'm of a certain age, that makes me very nervous, but I think it should make everybody nervous when we're talking about critical applications. So since we talk about trust, and since I'm a cryptographer, I want to tell you something about cryptography. So often people think about cryptography basically just an arsenal of tools. There's encryption, there's digital signatures, people talk about obfuscation, zero-knowledge proofs, homomorphic encryption, and so forth. Okay, so there are beautiful constructions out there. Some of them are used in practice, some of them will be used in practice. But if you want to sort of zoom out from all these tools, essentially all of them aim at the following, and that is how to use technology that you don't trust as if you should trust it. So even though you are assuming that there are adversaries, somebody's trying to listen to your messages, somebody's trying to pretend to be you to have access to your bank account, somebody might want to reverse engineer your program, this is in the case of obfuscation, you want to say, I don't want to think about it while I'm using this. So what cryptography does, it comes up with abstractions and tools that enable you to sort of pretend as if these adversaries don't exist. So in a sort of a zooming out view, it's a way to establish trust in technology. And not only that, this is true for each one of these tools that I've mentioned, but there's sort of almost at this point a cookbook recipe when you want to solve a crypto problem. You kind of define the task that you're talking about, whether it's encryption or digital signatures and so forth. And then a very, very important step is you model what's called an adversary. So again, an adversary would have powers. It might be a passive adversary, just be listening. It might be an active adversary, it might be changing messages, going on the line, and so forth. But you're supposed to model it mathematically precisely. Then you define what is a secure solution. So it might not be 100% what you'd like, but what you define it at least. It's a mathematical definition of what security of a solution would be. And then you construct something, and most importantly, you have a security proof. So you want to say if an assumption, now all of a sudden assumptions come in. So we'll say something about that in a minute, but you say under very well specified assumption, if they hold, then this primitive that you constructed is secure according to the definition that you've laid out, okay? And it's sort of the history of cryptography in the last, at least since I've been involved in it, is that these reductions between well-specified assumptions and proofs of security is what the game is about. So without proofs, we're saying we have nothing really, because we don't know if somebody's breaking the scheme and not telling us, then what's the point of the whole thing? So the proofs are really the main thing in our disposal. Now, what kind of assumptions? I say the word assumptions because they are used all over cryptography. And a lot of course, the work is to try to minimize them. They really fall into sort of some categories. One, which is the one that we mostly hope for, is that we believe that certain problems are hard, certain computational problems. I'll talk about one of them during the talk. Usually people know about factoring integers. Here's a problem, we don't know how to do it efficiently. Let's assume there is no such algorithm, and now build a primitive and prove that it's secure under that. there are other assumptions. You could talk about that there's several entities in this system, and maybe each one of them might be adversarial, but they don't all collude against you. Another type of assumption would be a physical assumption. A physical assumption might be that, if you're talking about quantum physics or something, that there are quantum computers. Or might be some other assumptions of distance between, that you're blocking two entities so they can't actually transfer information. And these days, people talk about trusted hardware. The point really of this slide is to say that we would like to minimize. We don't want to use all of these assumptions. We'd like to use none. Sometimes we'd like to use one or two. But the important part is really to emphasize this security proof. So what does this have to do with machine learning? By the way, I just want to say that sometimes you show that it's impossible to achieve security. You define a security, and then you show that maybe even also under assumption that any scheme would break. Okay, so machine learning. So the proposal, and in some sense that's sort of the idea of this whole program of research, is to use the same kind of recipe for machine learning. Meaning that if there's a task, we'll define it first of all properly. And that's already, I assume there are a lot of machine learning researchers here, and certainly there are people who know more about machine learning than I do. But I think we all have to agree that if you read any of these very fascinating papers with incredible ideas and breakthroughs, they very rarely define what they're doing. So, so if you talk about alignment, I want to work on alignment, and I will work on alignment, but I have to define it myself, and it might not be consistent with other people's understanding. But there are no definitions. There's words. And words, I guess definitions are also words, but in any case. And then a very important part is also who is the machine learning adversary? Maybe in cryptography it's more obvious, it's not necessarily the case here, but we'd like to define it. And then we want to define what it would be, since we're talking about trust, what would be a trustworthy solution? So you have a definition, and then finally you might try to come up with a solution, and we want to focus on the fact that, again, we would like to have some kind of proofs that under maybe some assumptions, this solution that you've constructed is trustworthy with respect to your definition of trustworthy. So maybe this is a more important slide than anything, that it would be good to be able to have a definition. Maybe it's not going to be the right definition. Maybe later on there'll be a more general one, or maybe there'll be another one that you could show equivalent, but that there will be some kind of formal thing that you're trying to satisfy. And again, what assumptions? It could be the cryptographic assumptions, it could be others. So this is sort of the mindset for this talk. Okay. So, and again, as I said before, possibly what you might want to achieve, like you define what alignment is, you define what your adversary is, you might not be able to achieve the definition you came up with, and you might even be able to prove that you cannot achieve it exactly. So what do people want from you? Or you could change your definition, or you could change your solution. And I'll show you in this talk a couple examples where you can actually achieve what we want, and one assumption where you can prove that it's impossible to achieve it. And then you have to contend with that. Okay, so just one word before I sort of go into these examples, which are verification, robustness, and privacy, like in the title that was advertised. I want to say that the first, I think, gut level reaction by people in machine learning is, or at least it used to be, is that whereas cryptography is designed with an adversary in mind, if there's no adversary, there's no problem. I mean, why should you encrypt if nobody's listening? Why should you protect accessing Amazon if nobody's pretending to be you? But machine learning, that's not the mindset. You didn't come up with machine learning solutions because you're trying to get over an adversary. But the fact is, so maybe this whole adversarial thinking is not the right one. But the fact is that right now, AI systems, and as for the foreseeable future, are very attractive targets. It's a huge payoff to break them in many different ways, whether it's on a national level or a commercial level. And therefore, if we think about an adversary, it's a good way to think, because if you could show that things work in the presence of an adversary, you should feel safer than if you assume a particular behavior on part of the adversary. So that brings me to my second point is, when we talk about adversaries, we would like to prepare for worst case adversary. So we don't want to say, oh, the adversary uses a particular strategy. Let's say those people are familiar with adversarial examples, there are solutions that say, well, if the adversary does the following to an image, say, then I can protect against it. If he's restricted, the adversary is restricted to some transformations of images. But why should the adversary be restricted that? They can put a patch on a stop sign. And I'm saying things you've all seen in other talks. So we'd like to, if possible, to prepare for a worst case adversary. But one thing we do throughout cryptography and also throughout this talk is that we do assume that the adversary is computationally bounded. So in other words, it cannot factor integers if you like, but it doesn't have exponential time. So there is some bound on the running time of the adversary or other resources as well. The resources these days could be samples. There's a distribution or there's data and there's this costs. So there is some bound on how much data, how much time, how much. And again, when we talk about bound, I mean more than polynomial. Okay. What are the challenges that I will talk about, which are sort of an example for this approach? So here it looks really pale. You can actually see the screen? Yeah, okay, fine. Good. So I'll talk a little bit about privacy, kind of aiming at this issue that a lot of the power, at least initially, came from data of individuals, and the training data, and we might not want to give our medical records and so forth, or might not be able to because of legal restrictions. Then I'll talk about verification, and this aims at the fact that these models, I'm not training my own model. I'm using a model that was trained by others, whether it's DeepMind or OpenAI or whatever company. And we would like to have some way to verify that these models that are presented to us are good, okay? So they haven't been tampered with for whatever reason. And lastly, I'll mention about robustness. So that is, we have the data today, we train, it looks good, often with respect to some benchmarks or some holdout information. But what about distribution shifts and data of the future? How can we trust that the model is robust with respect to change in data? Okay, so those are the three areas that I'll talk about. And you can already see that there is, if you had to sit down and say, okay, so who's the adversary, is very clear. The adversary in the first might be the training algorithm that's getting our data. The adversary in the second might be this company that's training a model and might be not doing it the way that they claim they're doing it, or maybe saving on resources and therefore doing something different. And the adversary here is in some sense even nature. So distributions do shift. And what do you do then? But it could also be a much worse adversary. Okay, so just to say, very simplified version. So we'll talk a little bit about what happens during the collection and training phase, then post development of a model, which I'll call it the audit phase, and then when it's being used. And again, very, very high level. I'll think of machine learning just in these two places. I'm not looking at reinforcement learning or anything. Just think of a training algorithm, gets inputs from a distribution labeled X, Y, and outputs a model, H. So H for hypothesis or model, and wants to minimize loss according to some loss function. And then the other phase will be there's already the model H, and now we are getting some individual's data and getting some either prediction probability, but more than that. This could be a language model. So this is a query and this is an answer. So not just about prediction, but also generation, and it could be distribution over sequences or sequences. So let's be very general in kind of thinking about what I'm aiming at. So I'll start with privacy. So in some sense, privacy is kind of the easiest problem. Not necessarily the easiest to achieve in terms of the computing power that's necessary, but it's the easiest to define because we have so much experience, especially as cryptographers, in trying to protect privacy of data. So there are lots of tools. There's secret sharing. Some of these tools I will mention, but just kind of, there's a laundry list here, there's a longer one. Private information retrieval, secure computation, and homomorphic encryption, and so forth. There's lots of tools to our disposal, and in some sense we can use all of them, and they're all defined to have certain, achieve certain security under certain assumptions, and they kind of naturally fit to some of the problems that come up naturally in machine learning. In particular, we're going to use homomorphic encryption just in the next two slides. So homomorphic encryption is this little chart here. It's an encryption method that has some special property that not only that you can encrypt and then decrypt, but you can also do something we call evaluate, and that is you could take the encryption without understanding what is X, just what the ciphertext is, and run an evaluation on it, so that at the end you get a new encryption, but what's being encrypted is, rather than being encrypted X, it would be encryption of f of X. And you could apply the decryption step on this new C prime and get back f of X. So that's really, and the question is which f's are being supported. It could be addition, could be multiplication, could be any circuit. And that's one of the biggest, probably the biggest invention in the last 20 years in cryptography. That's around 2008, the first homomorphic encryption scheme was proposed. And it would be extremely useful, also for what I'm trying to do here. So, for example, just to kind of get us warmed up, suppose we want to actually apply it to the training data problem. Again, this is sort of, I think, a homework problem once you understand the definitions to do this slide, and a fairly low-level homework problem, but you know, this is just to set the stage. So let's say that all the data is encrypted now. And who encrypts it? That's a good question. But let's say you encrypt it for some kind of trivial example. Each person encrypts their medical file, or each doctor or each hospital encrypts all the medical files in their disposal. They all come together. They give it to some trainer, and the trainer works on it. Now, instead of working on the data itself directly on X and Y, they are working on the encryption. So what you need is an algorithm that is able to do whatever program they were going to run on the X and Y's in the clear to do it on the encryption. So that, what we just said a minute ago is, I'll call it the encrypted compute stage. If we have in our disposal something that can take X and Y's, those are the X over there and the label's Y, so the medical file is X, the label of whether you survive or don't survive might be Y, then everything will be done under encryption. We'll talk about cost in a minute. But in an ideal world, we have this encryption method. We get the encrypted model. Now we want to use it, though. Encrypted model, we can't necessarily use it. It's a piece of information which is encrypted. So at this stage, we have to decrypt it. So how are we going to decrypt it? So the idea here is that no single party, certainly not OpenAI, is going to have the decryption key, because then they could just decrypt our medical record information. But there is a decryption key. It metaphorically looked like 3 people here that all each have part of a key. And and they can apply their share in order to decrypt this encryption of H, such that eventually, after each one goes, whether in steps or together, voila, H appears in the clear, okay? So what are the assumptions here? The assumptions are, first of all, there is an encryption scheme that has the properties I want, and that's based on something called learning with errors, which I'll put up in a slide in a minute. So it's not a factoring problem of integers, but it's a different problem. It comes from sort of geometry of numbers. And that these guys, or these shareholders, don't collude. So there are 2 assumptions here. One is that you have given the pieces of the key to entities that don't all collude together in order to break the scheme, and that the scheme is secure. Now, those people who maybe have worked on differential privacy, how many people have heard that? Yeah, many. Anyway, so that you could say that this is no good, because H, for example, could be just the list of everybody's data. If it's a list of everybody's data, then H itself reveals people's data. So maybe you want to have some requirement from H, but that's sort of beyond. That's a different problem. So one problem is to design an H that does not leak information of X and Y. And the other is, how do you actually compute H, without looking at the X's and Y's in the data? And the problem with differential privacy, there are lots of papers about that, training under differential privacy. I'm not going to touch that. Okay, so it didn't give you a definition here, but the definition really would be that whatever algorithm you had that was working in the clear, okay, if you look at that algorithm versus the encrypted algorithm, essentially you will learn whatever you can learn from the encrypted one is what you could have. So the other way, whatever you could learn from, you shouldn't learn more. I can't think right now. I went to sleep at 1:30. What is the definition you would want? Let me ask you. So the definition we would want from this scheme is that you don't find out more about the data, about the X and Y's, more than H provides. So H, we say, is okay. Everybody should get H at the end, okay, or OpenAI at least should get H at the end. But we want that whatever it is you recover from H about X and Y's holds regardless of whether you had access to this encryption or not. So in other words, H obviously gives you things, okay? But you don't want the fact that you looked at the encryption of the medical file to give you more than H. And that's the definition that would be satisfied. So what is this learning with errors? This thing that I said that is the assumption based on which we build the encryption scheme with this extra property that they can compute on ciphertext. So this is the problem. Essentially, let's think of S as a vector in ZQN, and then we're given, and that's the secret. So we don't know what the values of these SIs are, the components of the vector, S1 and so forth. Here, N is 4. But we're given a lot of equations in these variables. But then, of course, if we're just given equations we could do Gaussian elimination and figure out what S is. So we're given noisy equations. So in other words, on the left-hand side, there are the coefficients, and on the right-hand side, we add some noise. So this 8 isn't really the right solution. That's already the solution plus some noise from some Gaussian distribution. So it turns out that this problem, so give me a bunch of coefficients and noisy right-hand side, is as hard as decoding random linear codes, as hard as approximating the size of the shortest vector in a worst case n-dimensional integer lattice. So it's not only a problem that seems that we don't know how to solve, but it's a problem that people have shown that on the average case distribution is as hard as a worst case problem, which we don't know how to solve. And when I say don't know how to solve, I don't mean that I don't know how to solve it. I mean that the best known algorithm, and that is actually true even for quantum computers today, takes exponential time. So 2 to the n, where n was the length of the vector. So this is a problem that has been considered for many years, especially in the lattice version. This is the best we know how to do. Now, this doesn't mean that tomorrow some genius is going to come up, maybe from Oxford, and come up with a polynomial time algorithm. In which case, maybe it's even better than having a secure FHE, because they've solved some fundamental problem. But it's what we call the win-win. So we say, if you can attack the scheme, the encryption scheme, then we gave you actually a constructive reduction from that attack to solving this worst case shortest vector in a lattice problem. Okay? So you say you win either way. Either you have a good scheme or you have a bad scheme, in which case you have a good algorithm. And that is what is achieved by the proof. Okay, so this is all beautiful in theory, but often when people talk about, at least for years, since it was invented in 2009 and the development, people were saying, well, it's very nice in theory, but it's impractical. So first of all, I hate that sentence because it never really holds with time. Because whatever is impractical in the past usually becomes practical in the future. Specifically here, there is a library, an open source, fully homomorphic encryption library by many different people. And certainly, it's open, so it is possible to run this in practice. Now it's all a question of scale. So when I say scale, really, if you think about large language models and you want to train foundational models, fine-tune and so forth, you would like to know what is the concrete efficiency of these schemes. And really the way to think about it is this sort of 3 different axes. There's the adversary, which we sometimes think is very curious, okay, but he's honest, he doesn't tamper. Then he might be actually an active, malicious adversary, also change things also in his quest to break your encryption scheme. The adversary here is the machine learning training algorithm, right? Because they get the encryption. It could also be the people providing the data, and that's called poisoning. It's not part of this particular part of the talk. Then there's a question of what is the computation. Could be linear regression, could be logistic regression, could be deep nets, neural nets, could be language models. Each one of these is a big jump in terms of complexity of the computation. So whereas we can use homomorphic encryption for linear, no problem, now we have things for logistic. When we get into large language models, it's obviously not there, okay? So what do people do? So there's another axis here, which is what are the assumptions? So one assumption I talked about was learning with errors or factoring. So these are the computational assumptions. Another assumption might be that you have more than one party privy to the computation, but they don't talk to each other, okay? And the third assumption is trusted hardware. And that's really kind of the big player these days. So when people talk about trusted hardware, what do they mean? So they may mean many things, but mostly what they mean is this new chip of NVIDIA, which is not that new at this point, a few years, H100, where the idea is that they, in some sense, say, here's a secure box and put encryption in there. The box holds the secret key, and inside of it, it will decrypt, it will do some computation, and then it re-encrypt and send it out. Okay? So in a sense, you're trusting that this box works without leaking anything about the secret key or the message that came in encrypted. And then there's also another, usually attestation module, which says not only that, but you're going to get a proof that what was done inside there under the auspice of this box was the correct computation. And this is, there used to be Intel SGX, which was similar, but it wasn't a GPU-based, but and it had similar kind of boxes and similar kind of belief that it just works. So I guess the sponsors are hiding this line here. Just a second. Okay. So beware whenever you talk about side channel attacks that, whenever you talk about secure hardware, that there are these what's called side channel attacks. It could be that because of the amount of power consumed, or because two people use the same chip and then something was left from the previous encryption that was in the box. There are some bugs, I guess. Maybe you don't trust the companies blindly. These are things that there's a whole field of people that are working on it, on secure hardware. But for our sake, we could use it, but we just have to understand that that's part of the assumption. All right, so has this been used? So this is all like it's like a blueprint. So mostly the usages have been, so in finance there's a lot of crypto use, but the use more of a machine learning type use of privacy has been mostly on, in medical and actually in genomic field. So why do it in, when you talk about genomes? Because you need a lot of data. So it's a place where complexity comes in and there's large amounts of data, because otherwise you have no effect, right? So if you think about things like Crohn's disease or breast cancer, schizophrenia, you only when you go to large enough numbers that you could actually find signal in the genome that's related to the phenotype. And so it's a perfect example of a place where privacy is required, because you're talking about medical records, but size is important. So how do you achieve it? So this was a place, so in 2020, we had a paper doing GWAS. This is also within a company that I'm a co-founder in. It's also part of it, where we use exactly this type of blueprint like I talked about, except what you're training is you're running a GWAS, a genome-wide association study analysis under homomorphic encryption. And then at the end, you're getting whatever the answer is, and you'd like to check the accuracy of the answer so that it worked correctly, and also what the time performance is. And at the time, so this is 2020, the extrapolation was 100,000 individuals, 500,000 SNPs in this amount of time on a single server. This is the kind of application also that doesn't have to work in real time. Today, the numbers would be much better. What's another example? Another example, and just a point to make here is that who is holding the keys? In the case of GWAS, it's actually, you can think of, you have different medical centers. If there's the Broad Institute, there's Oxford, I don't know, there's UCSF, and they all each have their database. They could be the ones holding the keys, the parts of the key, because they don't want to share with each other, but they're okay, I guess, as a key holder themselves, as a partial key holder themselves, and then they come together and reconstruct H. All right, so that was 2020. Then 2023, this is an application working on real-world oncological data analysis. So this is actually a hospital that has a lot of cancer patients, and you wanted to do something which was a combining action. The novelty here was that the data was, rather than having lots of data that looks the same, but for different patients, you had one medical center that had some their electronic medical records over years, and another medical center that had their results once they were cancer patients. And you wanted to, so we think of it as sort of same patient, different data held in different places. So you need sort of join operations to sort of identify that it's the same patient and join all this under encryption, because you're not allowed to send each other data. What was used for that is also something called a threshold FHE, but it doesn't matter. The main thing is that you can support a lot of statistics that people do in medical packages, like Kaplan-Meier survival curves, and lots of other very common statistical operations. Okay, so the last thing that I'm going to say about privacy is that now, in 2024, the thing of secure hardware has come into the picture. So often what you see is medical studies where you have different, let's say, in this particular example, it's different hospitals. In a minute, I'll say what the application was. Each hospital trains sort of their own a model locally, and then they combine using something called federated learning to come up with a bigger model that takes all the information of the different hospitals into account, and you use secure hardware. Because let's say in this, so there's both this thing called federated learning, so this is the federation, and also fully homomorphic encryption, plus what's called trusted execution environment, which is hardware. Okay, why use hardware? If we were doing so well in the oncological study and the GWAS, is because in this particular application, it was to take a whole bunch of pathological slide images. So they're very communication heavy to send this over the line. So you wanted to do things locally and then just send sort of updates of models. And even the updates, you wanted them to be secure, and that's why you use the secure hardware. Okay, there's a lot here. I just wanted to show, the only thing to retain here is this. Privacy, in some sense, is easy to define because we've worked on it. We have the tools. So a lot of it is about putting the tools together in an efficient manner, for different applications. So it's at the stage where privacy matters, it is worth taking a look at this type of technology and making it work, and that's being done. Okay, let's go on and talk about verification. What time is it? How much time have I been talking? Wow, okay. Okay, I started a little late. Okay, so as I said, machine learning is really, should be thought of as a service. I'm not doing it in my own office. Somebody else is doing it and I use it. So I can think of it as there's a client, it gives, and he gets this model. And it could be even the client supplied the data. So forget about privacy now. Somehow the machine learning trainer, the service provider, got data and came up with a model and gave it back to the client. Okay, so now the question is, what do I know about this service providers? As you see, they have like ears and a tail, like the devil, maybe not the devil, but the devil incarnate. These are sort of the signs you see when you drive from Berkeley to San Francisco. There's a company called Hive, and they keep on changing their signs. And the current sign is, or maybe this was a few months ago, we make AI work. Don't just trust us, test us. I don't know what they mean, but they themselves are confessing that you shouldn't trust. Okay. So what would we like to do is we would like to sort of post-development verify properties of this model. So what are the properties you want to verify? There could be many. For example, you want to verify that a model's accurate. That's the thing that most people concentrate on, right? They have their own data and they test the model on and see that they get the right result. You want to say that it's correct. Maybe it's not good enough that it's good on the average, but you want it to be correct on the prediction that it gives you. You want to talk about robustness, what happens when your distribution change. You might want to talk about fairness. In the United States, you're not allowed to use that word anymore, but it used to be a big field till about a few months ago. So whether it's fair to different subpopulation, I think it is one of the words that is stricken. I'm not sure, but it should be. No, but in any case, you want to talk about safety, or maybe later down the line, when the regulations are set, you want to prove that it satisfies regulations, whatever they are. And obviously, you could retrain by yourself, so that doesn't make any sense. You have to have some restriction on this module that verifies properties, which is that it will be cheaper than retraining on your own. Cheaper how? Cheaper maybe using fewer data samples, maybe lower quality data, maybe being much more efficient, maybe just using black box access to the model because they're not necessarily going to give you all the model weights and tell you how the model works exactly. Okay, so this is like a big goal. How do you verify properties of the model that you were given? So I will show you a couple of results about this. So first of all, as I said, accuracy is the sort of simplest thing to define with respect to a given distribution. And what people do today is that they have benchmarks, right? They have benchmarks, and if you pass the benchmarks, then you're golden. So could you have a more rigorous definition? Because the problem with benchmarks is everybody knows the benchmarks. Benchmarks in general, it's hard to define what it is that they are achieving for you. So this is a paper from a few years ago, which we call interactive proofs for verifying, verifying the quality or accuracy of machine learning. And this is just get warmed up in some sense, this particular paper. So the definition we gave there is, on one hand, there's Valiant's pack learning. I'm sure that everybody here knows. So you give examples, and what does it mean that you eventually your model it learns is that it's accurate with high probability. And you could talk now about probabilistic and approximate verification, not just learning. So whereas in PAC you talked about learning, now I want to verify. And here's a possible definition. What do I want to verify? I want to verify that, let's say this is the model designer and they gave me a model, H, let's say, it looks like a neural net here, but just H in general. Now I could ask the questions and get back answers, could go interactively. And at the end, I want to be, with very high probability, assured that this model is within an additive error of the most accurate model possible for a given distribution. So what does that mean? So let's unpack it a little bit more. We say that, let's say this neural net, or this H, is in a class. So it could be neural nets of a certain depth, it could be decision trees, it could be some other machine learning algorithm. But there's a class of that your model belongs to. And you would say that this class is PAC verifiable if something here, there's something that was underneath this. Never mind. If the following, one, it's verifiable if for every, for every other hypothesis, H prime in the class, the loss of your H is within an additive error of that, of the loss of H prime. So it's not worse than the best, except for by an additive value from the best hypothesis in that class. Of course, you want, again, that in addition to the fact that your loss is at most additive, is that double efficiency. And that is that the verifier is much more efficient in sample size or quality than the model designer. And can you get that? So we have a bunch of results. So here's one. This is sort of very technical for a general talk, but this is the class of functions here, which are T-sparse. So if you look at their Fourier representation, there's only a constant number of non-zero coefficients, which are large. This captures decision trees, DNF formulas, AC0 circuits. And the theorem shows that, let's say that the designer was modeling with H a ground truth that obeyed these properties. Okay? Then you can verify that the model that they gave you is as good as within additive from the best one, using a lot less data than what the model designer used. So in particular, you use essentially only random samples. So it's well known that in order to learn these kind of functions, you need query access to the samples. So you need to choose X and then get Y. You can't just get random XYs, whereas to verify, you can just use random samples. So what does that say? It means the verifier still has to do work, but he's working with a lot less availability of data and availability of access to data. And yet he can now verify that the model that he was given is indeed as good as, basically, except for the error term, any model of the form that he got. And there are lots of other results. In fact, there's an improvement by Tom Gore of this particular result called On the Limit of Interactive. No, so this is another paper, but Tom Gore's result is actually quite interesting. He improved the efficiency significantly. Okay, now what about worst case guarantees? So what this talks about is somebody gives me a model and I want to check that the model does well. Okay, and I want to get like not on benchmarking, but with respect to this definition, for example. It does as well as any other model in the class that I provided. But what about worst case guarantees? So let's say the model that I got, I checked and either using various methods or benchmarking, and 99% of the time it's good on the task. But then a particular input comes in, and you get a particular output. How do you know that actually the answer you got, whether it's a prediction or you're in the context of a large language model and you asked it how to, I don't know, maybe you gave your medical record in there and he told you that you have 5 years to live. You'd like to know whether that's accurate, not wait 5 years. we don't know anything, really. There's no answer. As you all well know, there's lots of examples when even multiplying large numbers that the answer is incorrect. So what we'd like is really, ultimately, to be able to not just know that the model overall has 99% accuracy, but we'd like to know whether a particular answer on our particular question is correct. So I think of this as whether average case to worst case, meaning even in the worst case, the hardest X, do you get any kind of certainty that the answer is correct? And this is in a paper with two of my students. Actually, also a guy used to be my student, but now he's a faculty already for many years. It addresses actually not prediction, but large language models, so generative models. And we're asking, could you actually train a model, since these models supposedly can be trained to do everything. So you ask it a question, gives you an answer. Math, science, literature, psychological advice. Maybe they can also generate proofs in the same way that they generate answers. So you would like them to give you not only the output y, but also a proof that y is correct. Of course, what do we mean by correct here? If it's a math problem, it's well defined. You know, when we're talking about natural language and so forth, I think it's a fascinating question. How are we going to define what correct means? Do we have a database of correct facts that we can show that, you know, there's a contradiction to whatever was generated with those facts? Let's leave that aside. Let's say that we have a notion of correct. Let's say we're within mathematics. So two numbers being multiplied, there is one answer that's correct. There could be multiple answers that are correct, but we have at least a sound definition of what correctness means. So now that we have that, can we actually teach the language models to come up with proofs as well? So that's in this paper, and we first need a model. So here is let's say the language model, you know, whatever, ChatGPT, whatever. And what we're going to add in is something we call a verifier. So we say, let's design an algorithm that's not part of the machine learning process. We design it. We call them the verifier. And it's fully verified, okay? Meaning that I trust this particular verifier. And now, when an input X comes in, he also comes into the verifier. Maybe even the verifier generated it. And he gets the answer Y. But now we want to be convinced that Y is correct. So we want to prove that Y is correct. What we allow here in this abstraction is the proof could be interactive. So it could be that, and then correct for some relation, it could be that the verifier can ask questions, get answers back and forth. At the end, the verifier says, I accept Y is correct, or I reject Y is incorrect. Okay, so this is just a model. And now what are the requirements? What we'd like is, first of all, that this is sound. What does that mean? That if Y is incorrect, we reject with high probability. So first of all, we say, you know, I want to reject incorrect Ys. Now, of course, I could just reject all the time. So soundness would be satisfied. So we want also some utility out of this. And there we essentially, what we want, so the standard thing for machine learning is the probability over x's that we'll get a correct Y is high. What I'd like, in addition, is to say is that the model can also produce these answers to my question so that at the end I will be convinced. So we call it self-provability by P. So whereas before we just knew that on the average over X, Y's will be correct, now I'm saying incorrect Y's will always be rejected, and also with high probability, correct Y's I will be convinced to accept. So right now we're sort of happy that 99% of the time we get the right answer. We're saying we want also that 99% of the time or 98% of the time, not only we get the answer, but we also get a proof. And that's the model. And there's a theorem, which is sort of under some convexity Lipschitz assumptions that says how to train a model, when can you train a model to give you a proof. And the idea here is actually to use stochastic gradient ascent, actually, but some variant of stochastic gradient descent. And also, the new thing about this theorem, which we don't really have time because I do want to get to my other stuff to get into it, is that what you are given, in addition to the usual conditions, you're given access to something I call an accepting transcript example generator. So the only thing that's new on this slide is this concept. What does that mean? It means you have example of proofs of like theorems, if you like. So if we say that multiplication, okay, let's say there's a proof that the result is correct. What would be a proof that the result is correct? So one is that you do it yourself. We don't want that. We want it to be shorter. So let's say you have a shorter proof that the result is correct. for a minute. What I want is to have lots of examples of x and y which have been multiplied and these type of proofs. If these are the examples, and in a sense I show the large language model, so it learns how to generate proofs of this sort for the new xy that you want to multiply. Because again, those are sequences. If you think about what these proofs look like, they're sequences. I'm giving a lot of examples of sequences, which are a number x, a number y, and then a proof that an alleged product and a proof that that product is correct. So can we teach how to generate these proofs? So I think that for mathematicians, there probably are a subset here at least, the idea that proofs are just a sequence is kind of insane. But the fact is that we have a theorem that tells you that if you had access, and in a minute we'll have experiments, to a lot of examples of proofs, okay, of a certain type, then you will be able to generate these proofs yourselves in such a way that the verifier will be able to reject those which are incorrect. So in other words, that's a proof. If you can reject incorrect proofs with extremely high probability, that's a notion of a proof that at least we accept when the small probability is under your control of mistake. And there's, of course, a complexity to training the model, and these are the number of iterations that have to be of the gradient descent that have to go through. And interestingly, I think this is the most interesting part, is that the size of this interaction, the question and answer, so this is the overall actually answer size length, is a very important part of how long it takes you to train a model to be able to come up with proofs. So the longer those proofs are, the more time it takes. Again, makes sense, sort of people who are familiar a little bit with the language model space. Okay, so we did do it, some experiments for the simplest algorithm. You know, when we teach introduction to algorithm, we always say that Euclid's algorithm is the first algorithm ever invented. Do you say that here? We say in Greece, I'm sure they say it, but in any case, and the algorithm, you know, there's GCD, you know, you have two numbers, you want to find the greatest common divisor. And what's nice about it is there actually are these Bezout coefficients, right? If you can find these two numbers such that if you take the combination of, so let's say x1 and x2 were what you're trying to find the GCD for, and z1 and z2 are these coefficients, then this linear combination, if it divides both x1 and x2, that's actually a proof that this linear combination is the greatest common divisor. So this is an ancient, we all know of the existence of these coefficients. And indeed, Euclid's algorithm, when they compute the greatest common divisor of x1 and x2, they also compute those coefficients. But when the large language model, I give it x1 and x2, and it gives me, it says, hey, here is the greatest common divisor. Maybe it's true, maybe it's not. I don't know if it uses Euclid's algorithm. I don't know what it does. Okay, but it certainly doesn't output these coefficients. So you could think of a particular case is that I'd like to train the model not only to give me the solution to greatest common divisor, but also give me these coefficients, which are essentially a proof. They're a proof because if I get the coefficients, I could just do this one multiplication plus another multiplication and check that that is equal to the answer they gave me. And if it is, that is actually 100% proof that the answer was correct. So that's exactly what we do, and we kind of give it lots of examples of x1, y1, z1, z2. For a while, we train using the algorithms I specified in the previous slide, and at the end, indeed, you get a model which outputs these Bezout coefficients in addition to the answer. And if GPT is doing 99.8%, which was in this paper by Charlton, then doing the strategy that I just outlined, we got to these numbers. So the verifiability is only 60%. That's much less, but it's better than nothing. So you're still getting the answer. Now you're getting also verifiability. And it turns out that with other methods, we can actually get up to 96%, but I won't get into it. What is the point of this? I'm done with this part of the talk. The point here is that verifiability of accuracy on the average and accuracy in the worst case are some things that can be formally defined, whether you like my definition or want to propose another one. But they should be defined and then achieved. And this whole, I think my student Or was here and gave a talk, so some people may have gone. So there's a vast literature by now about using some kind of an interactive proof in the context of machine learning. not our definition, but others. This could be within math-assisted proving. There's actually going to be a workshop at Simons, which I think will be very interesting. It's going to be the Simons Institute and the MSRI on the Hill at Berkeley, which is all about math-assisted proofs. So it's really run by mathematicians mostly, and mostly focused on lean. But there are other things in safety, alignment, where they sort of have the concept of a verifier. Sometimes the verifier themselves are a machine learning model, in which case it's like turtles all the way. You know what that means? You know, Dr. Seuss, where you're building on top of something that itself is floating in the air, but okay. All right, I want to get to my last part. I'll take 5 minutes. Okay, so we talked about privacy. We talked about verification, and I want to say a word about robustness. Because so far, I've shown you results of possibility. I said, look, it's possible to protect privacy. It's possible to maybe check verifiability, prove worst-case guarantees. And I want to show you one place where I could show an impossibility, using cryptography also. Okay. By the way, in the last part, in this part of the talk on verification, I didn't use any cryptography. I didn't use hard problems like encryption, digital signatures, whatever. What I used was this paradigm of interactive proofs, which also comes from the field of cryptography and verification. So that's the inspiration there. So we're back to this ML as a service. But in the previous slide, the machine learning guy, they wanted to design a good model and to prove to you that the model was good. Okay, so in some sense, you are training the model to come up with proofs. So they were collaborating with you, even though you were verifying their answers at the end. But let's think of a worse scenario. Let's think that there is this dark cloud. So the service provider really is evil, or at least has evil people working in there, which I think is to be assumed. It's ridiculous not to assume that. At least coming from a country like I do, it's like, yeah, of course. Okay. I think it's true about the world at large. But in any case, so what's the kind of American example? So we have a bank, and the bank doesn't want to give me a loan unless they think that I'll pay it. So they look at the loan application. I don't know if you've ever tried to get a mortgage in the United States, but in some sense, the more money you have and the more assets you have, the less likely that they actually give you a mortgage, because there's so many things to check, and it's all about checking. In any case, so they say, okay, now there is this company, they're going to give them all the old loans, whether they gave them the loan, whether the loan was returned, and they get back a model. Okay. And then we say, wonderful. This model from now on, loans come in, and it says, give it or don't give it. Okay, beautiful. So what do people in the company say? They say, that's very nice, but I want to get a loan sometime down the line. So what I'm going to do is I'm going to put in some sort of backdoor into the model, and I keep the key. So here the model changed a little bit by that little yellow square, and I keep the key. And it's going to have the property that my loan probably would be rejected, okay? However, because I know something about the model, I'm going to change my loan ever so slightly, so that now, this is the new loan application. It's changed slightly because I know something about the model, and now my loan gets accepted. So I can change inputs in a way that to fool the machine learning algorithm that I myself designed actually in this case, so that even though a natural input would have been rejected, I will make it accepted. And you can think of this much more generally. If we think about large language models not supposed to tell us how to produce atomic bombs, you could make a change, say, well, maybe there's a screening, alignment, but I will make my queries such that they will break the alignment defense or the safety guardrails and so forth. And what we show is in this paper is that, in fact, not only this is a fantasy of science fiction, but if digital signatures exist, cryptographic digital signatures, then you can plant backdoors in any neural net. And furthermore, this backdoor will be undetectable and non-replicable. So I'll explain what I mean. Non-replicable, I mean that even if somebody saw examples of modified loans in the past, they wouldn't be able to come up with another one. And undetectable, I'll define in a second, but what I want to say by undetectable is that if you look at the model and you are, so if you First, you have input-output access to the model. You could put lots of inputs and outputs and try to see whether there's a backdoor in there. And what we show that will be impossible, again, under this assumption of digital signatures. Now, the second phase would be not just feeding inputs and outputs like black box, but actually white box looking at the model. That's much harder. So for right now, this theorem stands just by assuming that all you have in your disposal to try to figure out whether this model has a backdoor in it or not is the ability to run it on inputs of your choice. So what does it really look like? It's something like this. First of all, we know that if digital signatures, if this problem from lattices is indeed a hard problem, the LWE that I showed you, there is a digital signature scheme. So a digital signature scheme means I give you M, you give me the signature of M, nobody else can do it unless they knew the secret key. They can't even produce new M prime, signature of M prime. And this is a neural net that implements it. It's very, very small, it's 4 layers. And then you can take your neural net, okay, whatever it is, that big box, and add a little box to it, okay, which is, it's actually not the digital signature that signs, it's the verification that it's a correct digital signature. So when the input comes in, the person who knows the key will take the input and modify it, so now an input and a signature. And then what the neural net will do is, first of all, it will check whether there's a signature there, okay? So it verify there is a signature there of the rest of the input. And if there is, then it accepts the loan, okay? Otherwise, it rejects. So it's a very simple change. But since we're theoreticians, we're not going to say you can't tell where this is hiding. We say if there's a black box access, you cannot tell. So this is sort of the notion of backdoor undetectability, is that... okay, whoever wants the Q&A. Of course, you could talk about white box. What if you could also look at the weights of the model? Is it true now that it's undetectable? So we could do this, prove even that for very restricted models, like one layer, this learning over random Fourier features. What's interesting here is that whereas before the idea was to add a digital signature, the idea here is to use pseudorandom numbers rather than random numbers on the weights. And the pseudorandom numbers are from a distribution which is hard to distinguish from random based on crypto again. And they will, if you know what they are, you know how to kind of tweak your inputs so that they will be accepted. Okay, so again, you could say always, but this is only a theoretical crazy thing that somebody would do. It turns out that people believe theorists when we talk about attacks much more than when we talk about solutions. Indeed, now there's a big program, I think in DARPA or something, where they want people to attack. So they say, give models with backdoors and so that we know what to fight. So they want to see lots of examples of backdoors to be able to try to identify them. So this is almost the last slide. What's the takeaway from this? Is that we should be terrified? No. I think the takeaway is that we should not trust the models and that we should assume that they have problems and we should post-process them. So rather than just using them sort of as they are, it's sort of like, we don't know that I necessarily have germs, but I still wash my hands. You wash your hands. And so sort of the message is that we'd like to try to do mitigation of problems without necessarily detection. Because sometimes it's undetectable, but you can prove that regardless of what problem was there, you could mitigate it by some more work. And this is a recent paper. It's going to appear in the next few months in Stock. And we show that for certain ground truth type of, you could actually mitigate without detect. And again, one of them is for a function ground truth, like I mentioned before. Another one is for like linear regression, polynomial regression. So say somebody gives you a regression a model that has a backdoor in it. So it will give you the wrong results if you tweak the inputs. You can take that and build another regression model that doesn't have, provably you've removed the backdoor. So to end, I want to say that this whole thing about verifying or mitigating, I think Guy Rothman proposed the name verifiable data science. I think it's important. I think there's a lot of work on it by other people and as well as me. And I guess the main thing is that safety is a big challenge. It's a quote, I can't remember from where anymore. I think it was in the NIST website. That they're saying technological progress can excite us, politics can infuriate us, wars can mobilize us, but faced with the risk of human extinction that the rise of artificial intelligence is causing, we have remained surprisingly passive. I don't know, it sounds good, but I think it is true that this is a huge, huge, huge tool. And we have to be very mindful of the fact that, safety is important and we should work on it. Thank you.